health technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job to redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. And today I'm pleased to have with me in the studio Lynne Haas, a program manager since 2012 in DARPA's Strategic Technology Office. With a background in physics, engineering, and management, Lynne spends a lot of his time at DARPA thinking about a world without the Global Positioning System, a system which is all about physics, engineering, and the management of complex systems. And he thinks about bringing GPS functions undersea and to other places where GPS signals cannot now reach. In short, Lynne has become one of the agency's go-to guys in a technical area known as PNT, which stands for Positioning, Navigation, and Timing. Thanks, Lynne, for spending some time with me today.
Well, thank you for inviting me.
So before we talk about some of your efforts to develop Plan B for when GPS might not be available or to create an undersea version of GPS, I'm just interested in you. I want to find out a little bit about you, your background, and maybe something about how that background explains how you ended up here at DARPA in 2012.
Well, when I was growing up, I never thought about, when I grow up, I want to be a navigation engineer. That was not something that was at the front of my mind. However, when I came out of grad school, my first job was a navigation flight controller for space shuttle operations. And I fell in love with the art and science of navigation, and it's been a common thread in my career ever since.
Oh, what an exciting entry. I mean, to be working on the space shuttle program. Just say a little bit more about that.
When I was working on the space shuttle program, that was before we had GPS, and so the navigation system of the space shuttle used a variety of sensors to determine where that vehicle was in space. So the navigation system was primarily critical on the entry portion of the mission, that is when it returns from space to the landing field, but also ascent and on-orbit operations.
Okay, and what did you study in grad school?
Physics, and then I quickly learned that theoretical physics was not my forte, but I still loved physics. So my graduate degree was in engineering physics.
And there's one other thing about your biography, in a sense, that I'm interested in, and it's your name, because I believe your full first name is Franklin.
That's correct.
Though you go by Lynn, the second syllable for short. And most people who have the name Franklin and shorten it will go with that first syllable, Frank. So what's up with Lynn?
I like to think that my mother has a sense of humor. I am a junior, and she did not want two Franks running around the house. So my father goes by Frank. I go by Lynn.
So that indicates to me that there was a big dose of pragmatism in your home, and perhaps that spilled over into the way you work. So let's now talk about some of your programs. And I think we'll start with the Adaptable Navigation Systems Program, as do all programs at DARPA. This one goes by an acronym, in this case ANS. What intrigues me about this one, but I want you to say more about it, is that you are trying to tap into a huge diversity of signals here, things like signals in cell towers or TV signals that are already out there kind of in the constructed environment, but also other kinds of signals in the natural environment. The one that just really stands out for me is lightning. So let me stop there and just ask you to tell me and the listeners a little bit about the Adaptable Navigation Systems Program.
Okay. ANS is actually a portfolio of multiple programs. One of those programs under ANS is called ASPN, ASPN, which is short for All Source Positioning and Navigation. And it addresses the topic you referenced. We like to think of it as developing a navigation architecture and algorithm that can process what we call sensors of opportunity. That is, any sensor that has spatial or temporal information. So consider an aircraft. Primarily aircraft today use GPS, and the either standalone mode or they will integrate a GPS receiver with what's called an inertial measurement unit. That's basically a dead reckoning device, has sensors in it that senses accelerations and will sense rotational rates, and from that you can dead reckon. So the two GPS and inertial measurement unit combined form a very robust solution. But GPS sometimes is not available, and then that system will rely primarily on the IMU.
And Lynn, let me just stop you there. What are the situations under which GPS might become unavailable?
For ground users, GPS can become unavailable when you are in what we call urban canyons. That is dense urban areas, skyscrapers. Think of downtown Chicago or downtown Manhattan, where the buildings are obstructing the signals. Especially, and this is all in the context of maintaining very accurate navigation. Aircraft, especially military aircraft, when they roll over, turn upside down, now the GPS antenna is pointing to the ground. Signals aren't coming from the ground. Okay, so it will rely on the inertial measurement unit to dead reckon until the GPS receiver is exposed. And because the GPS signal is so weak by design, that it is very easy to interfere with a receiver's reception of that signal.
Okay, so actually that kind of sets up the problem for us. And
Yes.
now let me get you back to what you were talking about, which is to use sort of sensors of opportunity out there to make up for whatever loss.
So what we
might have
recognized was that many platforms we have sensors on them that are providing spatial information, but they're not being used by the navigation system. So the question we asked ourselves was, can we come up with an algorithm and an architecture that can be rapidly reconfigured to use sensors that are already on board our platforms to navigate when GPS is not available, or just as importantly, to provide redundancy and hence additional integrity to the GPS signals themselves.
Okay, and so work through a couple of examples of the kinds of sensing signals that you might use here.
One that we have used very successfully is imagery. Okay, consider aircraft with a camera looking at the ground. With the advent of satellite imagery, think of Google Earth. All those pixels in a Google Earth image have an associated latitude and longitude, and if we can correlate the image that is being observed by the camera on the airplane with that satellite, that what we call a geo-registered satellite image, we're able to determine where that aircraft is. That's part of the problem. The other part of the problem is, now how do I get that into my navigation system such that I can continually navigate with that? And that's what the Aspen program
Right,
did
so that's
for
where
us.
then you need that inertial measurement unit and a sense of timing combined with that imagery on the ground, and you can then start to keep track of where you are now and where you're going and so forth. Interesting, yeah.
Yes, but for ground users, for example, we are being bombarded with radio frequency signals where we are sitting right now, but we're not using them for navigation, but they have spatial information in them, whether they be TV signals, radio signals, or if we were outside, we would be receiving many signals from satellites. And so we call those signals of opportunity, and we've shown that you can navigate very well with those signals as well.
So just drill in a little bit on one of those signals of opportunity, lightning. So how does that fit into the picture?
That was a very fun signal for us. When lightning strikes, it essentially lights up the entire electromagnetic spectrum from DC to daylight and beyond. Researchers have shown that there are even X-rays and potentially even gamma rays coming out of a lightning strike. Tremendous amount of energy for a very short period of time. We're talking 1 to several milliseconds of duration and time. So, a huge burst of energy. The energy that is in the spectrum that we call the very low frequency band, VLF, which is the 10 kilohertz region, 10 to 20 kilohertz in general, that portion of the energy can travel around the world.
There's almost like a waveguide, right, between the Earth and the ionosphere, and those signals
that is
caught
correct.
in there.
That is correct. And the reason that's a waveguide is because at 10 kilohertz, your wavelength is now kilometers, okay, 10, 12, 15 kilometers. depending on what the exact frequency is. And because that, there's only a few wavelengths between the Earth and the bottom of the ionosphere, which is, depending on the time of day, around 80 kilometers. And you get a waveguide effect, which has very low signal attenuation. So the signal can be received at very high signal strength. And so the question was, can we navigate with those? So if we went outside and put a VLF receiver on the street or even in the building, you would be picking up tens of signals per second. The VLF portion of a lightning strike is called a spheric, short for an atmospheric. That's a fairly old term, but that's what we call it. So you would be receiving dozens of spherics per second. And so the question is, can you navigate with those?
This is amazing to think about navigating by lightning strikes. You have to know where those lightning strikes are in order for this to work, correct?
That is absolutely correct. And that is, in my opinion, one of the hardest parts of a lightning navigation system, if you will. To detect those, we use a network of what we call monitoring stations or reference stations located around the world that would geolocate those lightning strikes. Yes.
Right, and we've all seen these on weather reports where they're showing the lightning strikes from these kinds of sensor systems.
Many universities have lightning detection networks in place. There are commercial products for getting that information as well, yes.
All right, absolutely fascinating. So let's segue to another program you're working on, which was related to this one. This one is known mercifully in short form as STOIC, STOIC, but that actually is short for the long form name of the program, which is Spatial, Temporal, and Orientation Information in Contested Environments. But let's go with STOIC because it's easier to say. And this, too, has a deliverable of a backup GPS of sorts, and it involves a number of interesting-sounding components that I hope we can talk about briefly. Two that I'll mention are very low-frequency signals, which we actually did touch upon already when we were talking about lightning. But another component here is the development of optical clocks, which rely on quantum mechanical behaviors in atoms to keep super accurate time, and clocks are always a part of these kinds of navigation systems. We can't go deeply into the weeds on these things, but let's try to talk about them a little bit. Give us a flavor of what STOIC's about and what technologies you are hoping to develop to make it work.
Okay, let's talk about the VLF component first. It's interesting to note that the first global positioning system was not called GPS. It was called Omega. It operated back from the early 70s through the early 90s, and it was a VLF broadcast system, and it provided global coverage with only 8 transmitters located around the world. However, it was not accurate. That system generally provided 1-2-ish kilometer levels of positioning accuracy, whereas GPS is generally below 5 meters. So the old Omega system was clearly not accurate for what we now depend on today from GPS. So the primary challenge we have in STOIC for the VLF component is developing new models that can accurately replicate how that VLF signal propagates from a transmitter to a receiver, okay, such that we can get our accuracies to GPS levels.
And why the VLF, the very low frequency component of the full spectrum? You have many choices of frequency bands to use. So
you mentioned the waveguide effect, and we talked about the fact that the waveguide effect has significantly less signal attenuation such that the signal can be received at longer distances. So in the context of providing a backup system to GPS, that has global range. Clearly, we don't want to put a positioning beacon, if you will, every few miles around the Earth. So the ability to provide a positioning system with only a few, let's say less than 10 VLF transmitters is very appealing, especially when the signals can be received at very high levels.
Right, and there's probably pragmatic and cost issues. I believe VLF transmitters are often very big.
So they are. Not only are they very big, but they're also very old. It's in general, they are using 1950s, 1960s technology, and so using new technology. We're looking at ways of making them much smaller, more affordable, and more portable.
Okay, and then let's talk about the clock aspect here, in this case, optical clocks. And before you actually talk about the specific sort of quantum mechanical based clock technology that you're nurturing here, just for those who don't know, talk a little bit about the role that accurate clocks play in systems like GPS and other geolocation and navigation systems.
So there's a common phrase used in the navigation community, which is time is position and position is time. That dates all the way back to the 1600s, if not sooner, in the maritime days when we navigated off of the sun. When you left the port, whether it be, say, when you left the port at London, you would set your clock at noon, and then as you sailed across the Atlantic Ocean, you determine how many degrees longitude you had traveled by looking at the time on your watch, on your clock, at the point at which the sun was directly overhead. And you could correlate the number of the hours off of noon your watch said, not your watch, but your chronometer in this case, versus noon at London where you left, and from there get your degrees.
So the more accurate your clock, the more confident
case,
you could be of your position and determination, and the
correct.
less accurate, more
So in old days, it was very true. Time is position, position is time. With GPS, the same is also true. So the key to GPS is indeed the clocks. You are getting a ranging signal off of the GPS satellite. Okay, your receiver determines range. You don't measure distance. What you are actually measuring is time. How long did it take that signal to travel from the satellite to your receiver? So the satellite tells you, this signal left my antenna at time 1. You look at your receiver clock when that signal was received at time 2. And time 2 minus time 1 is the time of travel. Time of travel times the speed of light gives distance of travel.
And that's the key.
And that's where the range comes from. But it all goes back to the clock.
That speed of light, which we know and is constant, that's sort of the key here, right? Also.
Correct.
Without that, you wouldn't be able to, just from a measurement of time, know what the range was.
That is correct. And there are a lot of other things your GPS receiver has to do as well.
Yeah,
but that's primarily
when you really
it.
drill into it, it is remarkably complex on sort of every level by any metric you can imagine applying to it. So let's move now to a third program. This will be the last one I think we talk about. This one is known as Poseidon, and that stands for Positioning System for Deep Ocean Navigation. So it sounds like you're going for an underwater GPS system.
Yes. The bottom line, GPS does not work underwater. Actually, you can receive it at very shallow depths, inches. People have shown that, but that's not relevant to where we actually operate. We want to be able to navigate at much deeper levels. Poseidon is about bringing a GPS-like positioning capability to submerged users.
So when I think about submerged users, I don't think about radio operation there, though I know that there's some other real interesting work in trying to bring radio with VLF and ultra low frequencies down into underwater operation. But I think immediately of acoustic types of signals, so I presume that that's part of what
you are
is going
correct.
on.
The climate research community has been using low frequency acoustic signals for several decades now to monitor the temperature of the ocean as a function of time. And by using low-frequency signals, if you know, again, the analogy I just gave earlier, again, time is key here. If you know when the signal left a transmitter and compare that to the time you received it at another location, you can get the time of flight of that signal. Now, for underwater, so you mentioned for GPS, the speed of light is constant. That's not quite the case for underwater. The speed of sound underwater is a function of many things, primarily temperature, but also depth and salinity and some other terms as well. So we have developed models that account for all that. And in addition to that, the acoustic signals underwater don't travel in a single line between the transmitter and the receiver, which radio frequencies typically do. Acoustic signals will take many paths on the way from the source to a receiver because the signal is getting refracted due to temperature profiles in the ocean, pressure profiles, and things like that. So when you hear a signal, a low-frequency signal at a receiver that was emitted far away, you actually hear multiple instances of that. It's like an echo. In the RF world, we call that multipath. There are multiple paths that a signal will take.
So it sounds like with this multipath phenomenon going on, that one of the big issues here is going to be sort of how do you deconvolve all of those signals coming in? And so that sounds like algorithms. It sounds like computational issues just to make sense of what otherwise would be just a morass of acoustic signals.
You are correct. And that is exactly what we are focused on in the program initially is can we improve current models, develop new models that can accurately account for all of those paths that a signal takes such that we can extract an accurate time of flight and hence an accurate distance measurement. And once we get the distance from that signal, the navigation part is fairly easy. The hard part is the signal measurement model.
And just as GPS depends upon constellations of satellites, I'm forgetting the exact number now, but it's a couple of dozen. Do you know the exact number? I'm forgetting.
Generally, it's around 30.
Yeah, around 30. Would Poseidon and an undersea GPS system also rely on a constellation of acoustic beacons distributed through the oceans?
Yes, but hopefully not 30 for a given area.
Also in the ocean, is there a phenomenon like the one we talked about for very low frequency radio signals, sort of skirting the Earth through the Earth and the ionosphere and that sort of long waveguide effect? Acoustic sounds can travel tremendous distances in the ocean, right? I'm thinking here of how whales communicate over great distances.
That is correct, and that is the exact effect that we are exploiting. There is what's called a sound channel. The depth of a sound channel is in general a function of temperature, but in general in deep oceans it's about 1 kilometer deep, and so low frequency acoustics will travel for very long distances. There was a seminal study in the 90s that showed low frequency signals could be received in the sound channel many thousands of kilometers. I believe it was almost 9,000 kilometers away.
Absolutely astounding. Now, that also just brings another question to mind. I don't know much about how these beacons work and what their characteristics are. Are there issues of concern for animals living in the ocean where these signals will be propagating?
Absolutely. A key tenet of the program is we have to develop a system that complies with all the federal regulations protecting marine mammal life.
So, Lynn, I take it that one of the things that drives you is the concern that we have become utterly dependent upon GPS, just the way we were kind of utterly dependent upon the electrical grid. And we all know when the electrical grid goes down that we become frantic. Even 5 minutes of power out, we are going nuts. So GPS has similar vulnerabilities. Tell me about that aspect of how you think about technology and security.
Yeah, so there was a phrase that some people use. You have fail safe and fail operational. Okay, your primary system fails, it needs to fail to a safe mode, or you fail first to you're still operational, and then if it fails again, you're still safe. Okay, so you have that built-in redundancy. So you mentioned the power grid. Well, when the power goes out in the building, the diesel generators come on if you need continuous levels of power in that building. The same thing is happening in the navigation community. Consider autonomous vehicles, which are on the horizon. Clearly, they can't solely depend on GPS to tell the car where it is located because of some of the things we talked about earlier, such as they're in an urban canyon, they can't pick up the GPS signal. So you're already seeing driverless cars being more dependent on other sensors for providing positioning information, whether it be LiDAR, laser radar, or imagery, for example, or even the Doppler sensors you have on the vehicle. So you're already seeing redundancy starting to be built into systems that are going to be dependent on navigation in the future.
So when we think of the three programs that we've just talked about, ANS, STOIC, and Poseidon, and I should point out that you just handed off stewardship of this program to a colleague in the Strategic Technology Office. Can you give us a sense in each case of what the status of each one is?
So ANS is wrapping up. ANS is transitioning to the end users, to the services in various ways, and that's a good thing. STOIC is almost halfway through a 3-phase program. So we're in phase 2 of the STOIC program. So we've demonstrated feasibility, came up with an initial approach, generated evidence to support that approach, and in phase 2 we're now implementing that approach and doing higher fidelity data collections. Poseidon is just getting started. We are in the middle of what we call phase 1 of Poseidon.
Just one more question for you, Lynn, and that's, what question do you really wish I would have asked you that I didn't? And if such a question comes to mind, you can ask it now and answer it yourself.
So you mentioned optical clocks.
Thanks for reminding me. I should have pushed you. You didn't answer that question earlier.
So an optical clock it's an atomic clock, and we have atomic clocks today, such as a rubidium clock or a cesium beam clock. The cesium beam has been around since the 50s, if not sooner.
Just want to intervene for a second. A simple way of thinking about these things and why atoms can be clocks is because there are vibrations, oscillations associated with the nuclei, but rather than the kinds of oscillations you think about in a kind of old-fashioned clock with a pendulum. I mean, in some ways that's what's going on, but it's going on at billions and trillions of oscillations in what we consider duration of a second.
So in the atomic clocks of today, we're exploiting signals emitted by atoms in the microwave region, gigahertz level signals. Okay, gigahertz is a billion times per second. An optical clock is exploiting atomic energy level transitions that have frequencies over 400 terahertz, another 5 orders of magnitude. So that optical clock ticks 5 orders of magnitude faster than the atomic clocks of today. And by virtue of that, that's more precise time, and we get much improved stability out of that. Optical clocks today, in general, are about the size of a small laboratory. Universities have these optical clocks. NIST, the National Institute for Standards and Technology, has the world's most stable optical clock. DARPA in the past had a program that showed by making some trades in size, weight, and power and performance, you could reduce the size of that optical clock down to the size of a shoebox.
From a laboratory size down to a shoebox.
Yes, but that clock is still ticking at optical frequencies. Another DARPA program showed how you could make a very small and robust device called a frequency comb that acts like a set of gears and transfers that very stable optical tick in the 400 terahertz region down to RF frequencies.
Radio frequencies.
Okay. Then you can generate a timing signal that is used to systems of the day, type 1 pulse per second, 10 megahertz reference signals, 100 megahertz reference signals. So the STOIC program is integrating those separate technologies that DARPA developed into a single unit, such that I like to say we want to pull out the cesium beam clock and plug in the STOIC optical clock, and your time stability has improved by at least an order of 100. So imagine a clock that is able to keep GPS level time accuracy for over a year with no GPS receiver.
Fascinating. So thanks for giving us a flavor of what an optical clock is. I know that its complexities go off the charts, but I think you gave us a sense of what you're up to there. So thanks a lot. Now, Lynn, I also understand that in the not-so-distant future, you're going to be leaving DARPA. You got here in 2012. You will be leaving this year. You've got this amazing sort of skill set and mindset, particularly with these navigation technologies. We've been talking about atomic clocks, so sort of a whole range of abilities and skills in different areas. Do you imagine that you're going to keep applying that particular set of interests in your post-DARPA professional life?
Absolutely. Positioning and timing are built into so many systems we have today, and it's because of the success of GPS. Other nations are building their own satellite navigation systems as well. And GPS is embedded in so many things you wouldn't even think about. The ATMs you get cash from, GPS is in there. Electronic trading on the stock market, GPS is in there.
And just a point, in that case, it's mostly the timing function, right? Because you need to know when those transactions happen.
Agricultural, precision agriculture, GPS is in there. Power distribution through the electrical grid, GPS is in there. GPS is pervasive. I want to continue to enable systems today to provide that same level of positioning and timing with capabilities that are redundant to GPS to provide the integrity, but also going beyond the level of positioning and timing performance we get today with GPS, such that we can enable new capabilities that we can't even imagine today if we had that much more accurate timing and positioning information.
Right. So it sounds like exciting frontiers out there, and I'm sure you'll have no problem pushing on those frontiers. Lynne, this has been a fantastically interesting conversation for me. I feel privileged to have spoken with you for a while, so I want to just thank you for joining me in the studio today.
Well, thank you. This has been a lot of fun.
And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. For more information about Lynne Haas and his programs, and about DARPA's other program managers and the breakthrough technologies they're working on, visit darpa.mil. And to listen to or download this podcast, go to the Voices from DARPA page on DARPA's website.